Hello friends, welcome once again to an exciting video. So in the last video we have seen about the tokenization, right? So we are going through the Google paper, right? Understanding how the LLM works under the hood, right? So we have seen how we are providing the inputs. We have seen the input embeddings. Now we need to see about the positional encoding, right? So there is a request for you all. If you have not watched my previous videos, I would highly recommend to watch my previous videos, which is on input embeddings, right? It is really important to understand the previous concept before going ahead, right? So you will get the links in the pinned comment and in the description, both. Now let's understand the positional encoding. Right, so we have seen the vector embeddings. So in the last video we have seen the example cat sat on the mat and the mat sat on the cat, right? So how these two are different in the LLM world, right? So if we convert these jumbled words in the tokens, you will get exactly same, but you are seeing somewhat different over here, right? Because if you go on the tokenizer part and if you convert this into text, you will see that we are including space as well, right? If I remove the space and see only cat, right, and convert to a token, you will see 27899, right? Something like 27899, right? So it will be exactly same, right? So what things we have covered till now, right? So we have covered input, we have provided the input embeddings, right, in form of tokenization. Then we need to learn about positional encoding, right? So before going to positional encoding, we need to understand one thing, right? In this step 1 we have covered input. We are providing the input in the text format. It can be either images or document, right? Then in this step 2, in step 2 it would be converted to a tokenization, right? So tokenization, right, converted into number format, right? Now we need to understand the positional encoding, but before going to the positional encoding we need to understand one more thing, that is vector embeddings, right? So step 3 would be vector embeddings, right? What is this vector embedding means? So vector embeddings provide you the relations between these numbers. It provides the additional information, right? It creates a vector basically first it will create a vector. Now what is this vector thing, right? So first understand that when I say, suppose when I say India, so to know the vectors, let's take it a 2D vector graph for the simplicity, right? If I say India, so suppose India is somewhat placed here, right? So in the vector, right, I would say India is placed here, all right? And then if I say the food of India, chapati, right? So I would say chapati here, right? Or paratha. And when I say France, right, then the food of France would be located somewhere here, right? Suppose it is pizza, right? So how this vector embeddings form, right? So to understand this vector embeddings, each model has their embedding models. Now they work on the vector embeddings, right? So if I say India and you are saying paratha, right, you are going here. And if I say France, you are traveling in this direction, right, at particular angle, right? So in the same angle and same direction, if you travel, right, you will get the pizza, right? In the same angle and same direction, you will get the pizza. This is how the tokens are placed, right, at different positions in the vector, right? Now I'll say in India we are having Taj Mahal, right? So in India one famous monument is Taj Mahal, right? And now if I have to say France, so the famous monument of France is Eiffel Tower. So what is happening, right? So if I say India and travel upwards, you will find somewhat Taj Mahal. And at the same angle, if I travel the same distance, you will find the Eiffel Tower. So this is what called the vector embeddings, right? So why this comes into the picture? So to give you the relations. So what is relation between India and Eiffel Tower? It's a tourist place, right? If you want to search the tourist place, you need to go upwards, right? If you want to find for a food, where you need to go? You need to go right side, right? So this is the relation between the jumbled words, right, or the tokens, right? So this vector embeddings decide at which place you will keep the tokens so that it can be found easily, right? So this is what called vector embeddings, right? Now let's move further, right? The fourth step, positional encoding, right? So what this positional encoding means? So you have understood vector embeddings, right? So in the real world, it is not in the 2D graph. It's in a real world, it is in the 3D, right? So let me take this example, right? I have a beautiful picture over here. Let me zoom in for you. Right? So you can see the graph, it is in 3D, right? X-axis, Y-axis, and Z-axis somewhat on the on the top is the Z-axis. So if you start from here, you are saying a girl, right? And if you moving upwards to find the age, the relation is age, right? So you will find it woman. In the same way, if you are having a boy, in the same direction, if you move the same distance upwards, you will find a man, right? If you travel in this direction, right, somewhere in this direction, right, in this direction, you will find the gender, right? In this direction, you will find the gender, right? In the same direction, you can see, right? Woman, man, right? And if you want to travel in this another direction, right, in this royalty relation, so girl is known as princess, boy is known as prince, right? Man is known as king, woman is known as queen, right? In the same gender, if you want to find the gender from queen, you will move same direction here, right? You will find the same, you will move in the same direction, you will find the king, right? In the age to find the gender, right? So this is how this vector embedding means, right? It gives you the semantic encoding, right? What is this vector embedding means, right? So let's search about vector embeddings, right? So vector embeddings are neural representation, list, numbers or slash vector that captures the meaning, context and relationships, right? You need to notice this meaning, context and relationship of complex data like word, images and users. So what this vector embedding captures? It captures meaning, context and relationships, right? So it captures meaning, context and relationships, right? Vector embeddings along with the semantic search. Now it comes the positional encoding. What does this positional encoding tell you? So till now you have input text or images or document converted into the numbers, then you have converted into the vector embeddings. So positional encoding gives you the additional information about at which position these words are, right? And once you will pass through the positional encoding, it will recreate the vector embeddings, right? It gives you additional information, right? Let me write it down, and recreates the vector embeddings. So let me give you some demo on the vector embeddings for some more context, right? So I have searched about vector embedding visualization map. Let me open this, right? So now you can see here, right? This is a vector embeddings, right? If you zoom in, these are all words only, right? If you go here, right? So these are all words, and these are located in the 3D space. You can see x-axis, y-axis, and z-axis, right? So this is how the actual vector embeddings look like, right? It's very simple. It has lots and lots of words. You can see that car, foot, snake. If you click on the car, you can see all the other things related to the car, right? If you move in this direction, if you move in this board direction, right? How all these things are, right? So let me search here for car, right? Right now you can see car here, right? Carrier, right? So related words with this, right? So this is how the actual embedding look like basically, right? Embedding map, vector embedding map. So let's come back to our original discussion. The we have also covered now the positional encoding, vector embeddings. Now the next part, right? So we have covered inputs, we have covered input embeddings, we have covered positional encoding. Now this, once the positional encoding is done, right, after positional encoding, one more step is happened, right? Let me show you that. Is part of next part of the positional encoding. You can consider is at step 6. Step 6, right? You can say self-attention. Self-attention. So what does this self-attention, what this step do, right? So to make you understand, right, let's take an example for this. So if I say rain cloud, and I say AWS cloud, right? Now you can see at this point we have, this is a rain cloud and this is AWS cloud, right? But if you convert them into the token, the cloud word will be same, right? But how they understand that this cloud means something, this which rains, and this AWS cloud means, right, something which is server hosted remotely, right? So how these two things are different, right? Rain cloud and AWS cloud. In this way, right, to understand this self-attention comes into the picture, right? This self-attention comes into the picture. So the self-attention, what it does, it talks to each other, basically it talks to each other word, and understand what is exact meaning of each words, right, within themselves, right? Basically they talk to each other, right? So to provide more context, talk to each other to provide more context, right? To give you more example, suppose if you are fan of cricket, right? So let's take example of this, right? The first example can be flying bat, and the next is cricket bat, right? In this you can see the both bat are different, right? The flying bat means a bird which can fly, right? Something, a mammal or bird, right? Something. And cricket bat means, right, a bat with which you can play, right? So this step will decide basically self-attention, what it does is they talk to each other and provide more context, right, for each words. Now it comes the step number 7, right? Multi-head attention. What does this do? This step do, right? So let's talk about this step number 7. Once you say multi-head attention, right? So again, we will understand this with example. It will give you more reliable understanding, right? So yeah, suppose here a man, right? This is a man, right? Right, this is a man. One person sees, first you will see that you will say he is a man, right? So you will say he is a man. Next you will say this man is wearing a red t-shirt, right? Again you will see and you will say this man is walking, right? Again the third attention will grab, a man is walking on a bridge, right? So you are saying that a person is single, but how you are grabbing the attribute of that person, right? You are saying multiple things, right, for a single person, right? Like the same way, if you take the example of a cloud, right, you will, once it pass to the multi-head attention, it will grab all the possible ways, right, which you can think of, right? So this is the part of multi-head attention, multiple aspect of thing, right? So let me take all this down a bit, right? Now this part is completed, right? You have multi-head attention. Now the next part comes is feed forward. What does this mean, right? Let me write it down as step number 8, feed forward, right? So what does this mean? So feed forward, basically this particular thing, feed forward, is a neural network, right, which predicts the thing based on the previous inputs, right? It basically predicts the thing. You can write it down here. It is a, right, which predicts the thing. Now the next part comes here is, once the feed forward, you can see that this part is exactly same here, right, till here, the linear part, right? The linear part, step number 9, the linear part basically generates the probability matrix. It generates the probability matrix. Means how it was. Basically, if you say hi, it will generate hello, hi, how, right? So basically it gives all the whatever the possibility it has been predicted in a previous step, it will give a weightage, right? Some weightage to each of the word, right? Generated words, basically, right? To each of the word. Suppose it gives it to 90%, right? Now for hi it gives 80%, right? And for how it gives like 10%, right? So this is the work of the linear, right? It generates the probability matrix for the for the generated words in a previous step. Now the last step comes is softmax, right? What is softmax? Step number 10. Step number 10 is softmax. So this basically takes out the most accurate answer, right? Basically you can call it as, it takes out the most accurate answer. Right? In this case, if you see in this case, what it will take for hi, the most predictable answer is hello, right? So it will take the hello, right? So this is how, right, one iteration is completed. For high input high, it has done all these 10 steps and then predicted hello, right? Now again you see outputs here, right? So again what will happen, how will be inserted inside here, and the same thing again and again and again, the iteration will go on, right? This is how we have explained in my previous video, right? So if you have entered this, right, not here, somewhat here, right? So in my previous video, so if you have entered hi, first it will print hello, and then hi hello will be entered again then it will print Aditya, then again hi hello Aditya will be inserted, and this iteration keep on going, right? So this is how the one iteration we have completed. Again and again this iteration will go until unless it thinks that things are okay. You will get at the end, you will get end keyword or something, this stopper, and then it will stop there, right? This is how the complete architecture of the LLM, right? This is how LLM works basically behind the scene. It is based on the transformers, right? So I hope you have enjoyed this in-depth session of transformers about this Google paper, Attention is All You Need. And I hope you have understood how the LLM works behind the scene, right? So going forward, we will use the LLMs, right? We will not go in depth of all this, right? Doing positional encoding, self-attention and all this, because we will use LLM directly as the application developer. We will use the LLM and we will create the agentic AIs, right? The agentic flow, other flows, right? So for that, stay tuned for upcoming videos, and for that you have to hit subscribe if you have not, and don't forget to like this video. Have a great day. Bye-bye.